My kit's all completed. It took a while to assemble it, but it was worth it, and we're ready to do some testing to see just exactly what the output looks like. We have a little extra noise here because I'm running a muffin fan over here to keep the finals cool, because we're putting out steady carrier here, and right at the moment it's about 16 watts worth of carrier. And over here we have the spectrum analyzer output, so we'll go through each one of these items and explain what's happening on each of them. Took me a little while to get it operating right, and it wasn't its fault, it was my fault. I went through the instructions one time and set up all the biases and tried it out, and it didn't seem to work right. It seemed insensitive to modulation voltage. So this morning, before I started re-engineering, which it seems like that's always a step you do, if it doesn't work you blame the engineering. In this case, I just went back and realigned the bias levels in the PA, and it made all the difference in the world. If you look over here on the right, maybe you can see it, I've got 50 volts peak to peak of modulation voltage going in at 1.5 kilohertz, and coming out over here on the scope I have 80 volts, and we're at 14,251 is what the counter says. So everything's working just as it should, and if you notice on the scope, it's nice clean output. Let's take and look at things in a little more detail. I have my modulation being applied here to the mic jack. I don't have the resistor in for electret mic because I plan on using a dynamic, so there is no DC voltage here at this point. If you installed a resistor and plan to use an electret mic, you need to make sure that you couple into the microphone jack using the capacitor to block the DC voltage. I've got a dummy load hooked out here at the antenna jack. I'm soldered on coax with the on the bottom of the board, so make sure that when you test you use that dummy load. I noticed earlier at 16 watts I've got a big dummy load, a 50 watt dummy load, but I can get it warm even with my little 16 watts here, so need to be aware of that. Also, what you want to watch is the temperature of the output devices. They will get warm, even running 4 or 5 watts, warm to the touch, almost hot if you're not using the fan. Using the fan here that I'm using, they stay very cool even running it with a continuous 16 watts output. There you can see the fan doing its job. It's just a 110 volt muffin fan. It wouldn't take anything anywhere near this big, but this is what I had. It was easy to get to, and it's doing the job well. You say, how do I know I'm getting 16 watts out? Well, you can calculate it easy, and it's using the scope is a good way to tell. What we need to do is take the peak to peak voltage, which is in this case is 80 volts because I'm running 10 volts per division there, and there's 8 divisions in amplitude. Divide that by 2 to get peak voltage. So we got 40 volts peak. So convert that to RMS. 40 volts times 0.707 is equal to 2828. We're going to square that because power is equal to E squared over R. So we square it, and that's equal to 799.75, which is pretty close to 800. Then we're going to divide that by the impedance, which is 50 ohms. We have a dummy load that works out to be 15.995 watts. So that's how you can calculate your power if you don't have a watt meter. Actually, that's probably more accurate than any watt meter because the oscilloscope accuracy is going to be very good at 14 megahertz for most scopes anyway, especially if you have a higher bandwidth scope. So it's nice clean sine wave. We don't see any crud or anything else, and I can take and decrease my drive. So I go down to 40 millivolts in, and it seems to be stepping down. Sure, lose my trigger. Seems to step down linearly. And that's with 10 millivolts of drive, and I'm still getting 20 volts out. One point that I always remembered is with 50 ohms system, 40 volts is 4 watts. So here I have 4 watts out at this point, and I'm putting 20 millivolts in. 30 millivolts, 40 millivolts, 50 millivolts, and I'm getting 60 watts out, or 16 watts out. Here's what the spectrum analyzer is telling us. Here's our upper sideband. We can set that to a gradical marking here. And this is our carrier. So we have 10, 20, 30, 40, 50 dB, over 50 dB of carrier suppression at this time. And up here is our second harmonic of our modulation voltage. It's down 10, 20, 30, 40, 50 dB also. Here's the third harmonic. It's about 45 dB down. And here's our lower sideband. It's down 10, 20, 30, about 38 dB down. So that's all the components of the waveform, and it's still sitting over here running cool with the fan on it, and you've seen it's been running for about 5 or 10 minutes now, steady, with putting out 16 watts. So let's take and do a couple things. If we take and decrease the modulation voltage, if I decrease modulation voltage, I'd expect the power to come down in the sideband. So we'll step down to 40. See it drop down a little bit. 30, 20, 10. When I drop down to 10, I've lost about 10 dB of power output. So that should be about 1.6 watts. It doesn't look like it changes much, but on the screen, remember, each one of these little tiny divisions here is 2 dB. So every time it moves that division and a half here, that's 3 dB difference. So we'll step it back up to our 50 millivolts input. And it seems to be stepping up fairly linearly. Hopefully it's not running into any compression. I notice on my power supply at this point, I'm pulling 2.04 amps of current at about 12, I'm at about 12.4 volts. So my power supply is going to start limiting out. It's only rated at a 2 amp output. So if there's any compression going on at the last step from 40 to 50 millivolts, it could be because of the power supply also hitting up in its limit. But the waveform really looks pretty clean. See, how do you adjust it without having all the fancy equipment? Well, if you have a scope is a basic equipment that would make it relatively easy, and a signal generator. With a scope, you can measure the output of the signal generator and set it to 10 or 20 or 50 millivolts. In this case, 50 millivolts seems to work real well. It should give you the drive all the way through. You can set it, put 50 millivolts into the mic jack, and start aligning from that point. I'm going to misalign this a little bit so you can see what happens. I've reduced the modulation voltage in to 20 millivolts simply because it gives me a better display on the screen. We can see the full waveform easier, and also there's no sense misaligning something at full power output. If we look at that, you notice we still have 4 divisions peak to peak, so that's 40 volts. So we're still running at 4 watts. So what I'm going to do now is I'm going to misadjust the carrier balance pot. What it does is suppress the carrier, and that's one adjustment you'll have to make, and that's R66 on the schematic. And what's going to happen is we're going to lose our nice clean sine wave, I believe. See what's happening at the peaks? That's carrier being fed into it. So if I was to adjust this way, just using the scope, I could probably come and tweak this and get it started just by watching the oscilloscope output there. The other way to do it is to remove the modulation voltage, and we'll do that. So what you would want to do right at this point is adjust R66 and C65 for the cleanest looking waveform if you're going to do it this way. That'll get you in the ballpark. So let's work it to where we get a little closer yet. What I've done is remove the modulation input, so that with no modulation input I should get no carrier output or no sideband out, and I should also get very little carrier out. So what you're seeing on the screen is carrier. So I'm going to come back and adjust it at this point, and it's very sensitive. You know, so if you look here, I've got the scope set to 200 millivolts per division. And I can also adjust the capacitor there. Notice it has a big difference, makes a big difference. And we're just barely tweaking anything here. There's about 200 millivolts out. We can calculate the carrier suppression at this point, and at one time when I saw this, when we were adjusting, I had it down to probably 200 millivolts. That's awful. That's awful close. We probably got 250 millivolts there. So if we take the 40 volts, which was we started with, take 40 divided by 0.25, it gives us 160. If we take the log of 160 and multiply it times 20, we have 44 dB of carrier suppression at this point. So that's one way we can do it, is by just looking at the output of the transmitter with no modulation applied, or to adjust it for minimum. Or you could take the output with some power coming out and adjust for a clean sine wave. So let's take a look and see what we were actually doing on the spectrum analyzer. First, I'm going to hook back my modulation, and we have our nice clean sine wave back, and it's about 40 volts peak to peak. So that says we have our 4 watts back. So let's move on over to the spectrum analyzer. We just got through tweaking, and I'm not going to tweak a thing. I'm going to just look at the spectrum analyzer output and see what it looks like just after the method we just used. Now looking at this, you're going to accuse me of cheating. I did not cheat. This is actually the best carrier suppression I've ever gotten set up. So let's set it up to a gradical marking here. This is the carrier right there. It's almost totally non-existent. There's 10, 20, 30, 40, 50. Better than 55 dB of suppression. Here's the lower side band. It's 10, 20, 30, about 36 dB down or so. The second harmonic modulation is down 10, 20, 30, 40, over 50 dB. So that's all great. Third harmonic, there's next to none. Now this is at 4 watts output, and I have 20 millivolts input. So I'm going to bump it back up to 16 watts output. And there we are. We'll adjust back up to a graticule, and you'll see carrier suppression is still real good. It's still way down in the mud. Second harmonic is still down. It's down 10, 20, 30, 40, 50 dB, which that's really good because we went through a period of investigation a few months ago on the forum where we were getting a lot of second harmonic output in when we modulated the original Bitx circuit, and that's why they came back and redesigned the microphone circuit. So this looks great. I'm real happy with the output, and the next thing is to get the receiver going. I'll make a tape in a little while, probably in a week or two. We'll go through the board section by section and look at the voltages that you might expect to find, so that section by section you could troubleshoot your circuit if you're not having the luck that I have.